Well, we're very happy to have Rashmish, who's going to tell us about holographic phase transitions in the early universe.
Thank you. Thank you for the invitation. Thank you for having me here. This is the first time I'm here in Moyu. Right. So today I want to tell you some work I've been doing with Lisa over the past 2 years, I believe at this point, investigating holographic phase transitions in the early universe. And this talk will be based today on 2 papers we put out recently, one last year and one earlier this year.
Click on the screen. And then arrows.
Oh, okay. Okay, so just some broad theory, just some broad motivation. Strongly coupled theories appear in many VSM directions. Traditionally, they were thought of for Higgs naturalness or fermion mass hierarchy. Now people think about them in the context of dark matter, dark sectors, axions, and whatnot. The phenomenologically relevant theories are confining theories, usually with a small confinement scale compared to the cutoff of the theory. And this is generated via dimensional transmutation like QCD. This, for example, is utilized in composite models, partial compositeness, and all that, right? And this whole framework is related via ADS-CFT, the bottom of holography, to RS framework, which uses warped and de Sitter space in 5 space-time dimensions to provide a geometrical way to understand these questions. So the early universe cosmology of this scenario is actually very interesting for many reasons. One is that depending on the energy scales involved, the confinement deconfinement transition can happen in the early universe. And the gravitational picture involves thinking about space-times with horizon, because as I will explain in the following slides, that the deconfinement phase corresponds to usually a black hole in the space-time picture. So this gravitational picture involves the space-time with horizon, and this transition, this confinement deconfinement transition, is analogous to the Hawking phase transition that people study on their own right. And again, depending on when certain conditions are satisfied, there can be detectable signals, gravitational waves, and many other signals. And these things have been studied a lot in the past 20 years, but hopefully I will convince you by the end of the talk that there are some surprises and some new things that people have completely missed, and I will also explain why I think they were missed. So these questions are interesting, and I will use the RS framework to examine some of these questions. But the questions are more general in the sense of all strongly coupled theories and what are their cosmological history in the context of phase transition. And please feel free to stop me anywhere if something not. So a general prediction in this in scenario is that there is a period of supercooling. Supercooling means that you are stuck in the wrong metastable phase, and so it's like we know about what happens with water, that you go past 0 degrees Celsius and it stays water and not ice. So a generic prediction is that there is a period of supercooling when the universe undergoes accelerated expansion, and this is due to this supercooling is because there is a small rate of transition from the deconfined phase to the confined phase. So I'm thinking going from the deconfined phase to the confined phase, and the universe gets stuck in the deconfined phase. So here's a cartoon. The time runs that way and temperature runs this way, and this is the confinement scale. We expect that at high temperatures the theory should be in the deconfined phase, and at low temperatures the theory is in the confined phase. Now, if it is true that there is a period of supercooling and the theory is stuck in the deconfined phase, there is a problem with fitting with the standard picture of cosmology, because at some point we go to the Vivian temperature, and if the theory is still stuck in the deconfined phase, there's just too much radiation, right? So this is going to muck up the whole story. And this is usually if you take, for example, the confinement scale to the order tens of TeVs, which is how all these theories are thought about traditionally, and then MeV is not too far from TeV. Of course, alternatively, if the phase transition is happening in decoupled dark sectors where this doesn't have to be, the electroweak scale or whatever, the rate and the supercooling is relevant for estimating many features of the dynamics. For example, gravitational waves, and people have argued that it can be a way to form primordial black holes and whatnot. Okay, so this is just to give some broad motivation that why these questions are relevant. And now I will, so in the work that I'm presenting today, we will revisit some of these aspects, and we will see that there are some changes than what people have thought about. So now to get into the details, the confined, the deconfined phases in this RS way of thinking about strongly coupled theories correspond to two solutions of Einstein's equations, so two space-times. By the way, this and a couple of slides will be based on this almost 20 years old paper by Eminelli, Nicholas, and Latazzi, which is the first paper which set up this problem.
By ohms, it's more than 5 ohms.
Yeah, 2001, I think.
Yeah, so it's 24 now.
3 years. Yeah. I want to reduce it, but yes, you can call it 25. 25. So these are the two solutions of Einstein's equations with a constant negative cosmological constant. One is just the usual metric you might have seen. This is the RS metric, where this coordinate R goes from 0 to RIR, and it's chosen in some way. And the picture is this. So there is the boundary of the area space, which is denoted by this. There is a UV brane with some some tension which is placed at R equal to 0, and there's an IR brane at some R. And usually it also needs a stabilization mechanism, which will be relevant in the story in the next couple of slides, but for now we don't need to think about that. So this is dual to the confined phase. There's another solution which is which has a horizon, and the metric looks a little bit different. And now we still have the dotted line, which is the area's boundary. There's a UV brane, but now there's a horizon at some point. Horizons have a temperature because of Hawking temperature, and this temperature corresponds to the temperature in the dual theory, which is what the deconfined phase is, because the field theory is at some finite temperature. And that can be calculated by many ways, and it's given by this expression. So the temperature is related to the parameter RH. And when RH goes to infinity, temperature goes to 0, and that's like not having a temperature at all. So if you want to understand how does the transition happen, we should think about the free energy of the two phases and understand when does one free energy become favorable compared to the other. And again, let's ignore the stabilization, which is kind of crucial, but for now let's just do it without that. So without a stabilization, we can calculate the free energy. Free energy is UV divergent, like many quantities in field theory, so you have to regulate it. Or one way is to look at the difference in the free energy of the two phases, and free energy can be calculated by looking at the thermal partition function and looking at the dominant saddle, and with the computation yields is that the free energy of so BB refers to black brane, which was the deconfined phase, which I introduced in the previous slide, and this is the RS. We find that the free energy is given by this quantity. So there's a T to the 4th, and there's a negative sign, and there's this is a 5D Planck scale with some numerical factors. The crucial point is that free energy is negative at all temperatures. Okay, so this is saying that the black brane phase, or the deconfined phase, is always the thermodynamically preferred phase. Of course, this is where the stabilization mechanism becomes important, because without a stabilization mechanism, there is no confinement scale to begin with, right? So this is why this topology. And so there are many ways to do this stabilization. One can have a 5D field which introduces a potential for the IR brane, and you get a stable geometry. So without a stabilization, there is a modulus that you can identify, usually called as a radion, denoted by this V5. And so without stabilization, it has a flat potential. With stabilization, which is again some 5D dynamics that you throw in, there is a non-trivial potential. Now with the radion or the stabilization included, you can revisit the free energy calculation. And now what you find is that at the minimum, so at the two solutions, the RS solution and the black brane solution, you can calculate the free energy. And you find that the free energy now is shifted. So instead of just having the minus T to the 4th part, there is another contribution. And now you get something which is more realistic. You find that the free energy is 0 at a critical temperature. So there is a non-zero critical temperature. If the temperature is more than a critical temperature, the black brane geometry is favored, because the free energy difference goes one way. And at below the critical temperature, the other one is favored. So, and then depending on some explicit models people can write down, the expression for critical temperature depends on the model. So, you can come up with some explicit models, not super relevant. What is relevant is that the critical temperature is always smaller than the confinement scale. There is some parameter that sits. This parameter is the one which appears here, which is the 5D parameter, and it's usually taken to be small. So the critical temperature is smaller than the confinement scale, at least in the models that people have studied. So far so good, but then this was still question of statistics, right? So statics, right? So temperatures higher than TC, temperature lower than TC. But how do we calculate the dynamics? So this was pointed out in that paper by thinking about the free energy off shell, both for the confined phase and for the deconfined phase. And again, there are some technical details that I'm going to skip, but we can go over them again. They map the problem, the dynamical problem, to in the limit of just thinking about the radion to a vacuum tunneling problem in field theory, which we know about. Okay, so they said that there is a shape of the potential on the confined side, just corresponds to this phi, this radion, and that's why I'm in the radion picture. And then there is a similar potential and a minimum one can think about on the deconfined side. Notice that this is not phi on this side. There is no phi on this side, so it's a little bit different. And then as I will explain in the next couple of slides, the dynamics just becomes how do you go from here to here. So that was an oversimplification. There are some details. The first one is that this shape is very asymmetric. Remember I said in a couple of slides back that this critical temperature, at least in the models that people have studied, is much smaller than phi min. So the shape actually looks more like this. One side is much bigger than the other. The second difference is that depending on the temperature, this side changes. So that makes sense because at high temperatures, you are stable. So this is the more stable place. At critical temperature, the two vacui are degenerate. And at lower temperatures, this is metastable, and now you're going to tunnel from one place to the other. Another crucial thing is that if we want to match, for phenomenological reasons, if this is the place where the CC should be 0, then this is the place where CC is not going to be 0. And that was the statement before that the false vacuum inflates. Right? So if you're in the wrong vacuum, once you cross the critical temperature, it's going to experience accelerated expansion. So you have to calculate the phase transition rate, and you have to compare it to Hubble. The Hubble is dominated by the vacuum energy density, and so there are estimates that you can write down. And then depending on the rate, the phase transition will happen at some temperature called Tn, nucleation temperature, which will be smaller than the critical temperature. If the nucleation temperature is much small, that's the period of supercooling. Right? So if it happened right at Tc, you would say it's a quick phase transition. If it happens much later, there's a period of supercooling. And if Tc is order Tv, Tn should not be Vn, otherwise this makes no sense.
Sorry, I'm
yeah.
confused. If it happens much later,
Yeah.
then it really doesn't happen, right? Because the universe just become eternally inflated.
Well, so the rate is not 0. At some point, if this condition is satisfied.
But the question is not whether it's non-zero, but how it is compared to
The Hubble. Right?
Hubble, right?
Yeah. So in the minimalist models, which is what this paper was trying to do, is that this is never satisfied unless you are completely out of theoretical control.
Right.
So they will say that then you eternally inflate, right?
Right.
So this is completely dead.
Mm-hmm.
But as I will explain in the next couple of slides, there were some assumptions that they made for calculational simplicity. If you relax that, you can satisfy it. Basically, what they did is they did their computation at T close to T critical. Okay, and then they said it never happens. But when T becomes smaller and smaller than T critical, you have to revisit the problem. And now you can, but now there is a problem that it shouldn't happen too late. If it happens too late, then it's interesting on its own right, but it's not going to fit with the picture of cosmology that we have.
Just it feels that it's a little bit tuned, given that typically this rate is exponentially sensitive to, so it's tuned to be to happen late, but not to be an eternally inflated.
Is there a window that is?
Right.
Yes. So there, it
looks like that window is kind of exponentially
sensitive.
small. Right?
I mean, this is the challenge of making these models viable. That it has to happen in a very specific window, otherwise it doesn't happen.
Isn't the barrier shrinking as the temperature decreases? At least naively in this picture.
So that helps. That's why the rate. So again, these things will be more precise later. But the rate is a certain function of temperature. And the rate starts to increase as the temperature goes further down, right? When you're not in the thin wall limit, which is that the two vacui are degenerate. Mm-hmm. When you go here, let's say, right, then there's a much smaller region of classically forbidden part that you have to tunnel, so it helps. But that will be exponential. That will be logarithmic compared to something else, so it will not help tremendously. And because there are so many parameters, in the end, you know what I'm saying?
No, I think they forgot the meeting.
I should try to make it.
Also, last question, can you remind me, because as you said, like this picture is a bit like impressionistic in the sense that on the left hand side there is no really that field phi.
Yes.
So how does one then estimate the rate? Because
Yes, so this will be the next slide.
Okay.
This is part of why this is an oversimplified statement to say it's just a tunneling problem, right? Because there are a lot of things that you have to include in things. So the next thing is that all this picture is at a finite temperature, right? This whole calculation is done at some finite temperature. So when I wrote down and I said that the free energy is just the potential of the radion, well, not true. At some point, the finite temperature effects will change the potential. Right? Similarly, the finite temperature will, I mean, this is not even the same axis. The phi is not even the same thing on this side, right? And so in principle, and this will be relevant for the second part of the talk, if we get to that, is that you expect this picture to change violently, at least in this box, because at some point the temperature will become of the order of phi, right? So if you fix the temperature, phi min is much bigger than the relevant temperature, but at some point, you're sensitive to very small phi's. So now your potential will change on this side and also on this side. So the proposal was, since the shape is so asymmetric, there's a way to estimate all this by saying I don't care about all this part, okay? Which is effectively saying that you just tunnel from like a step function to this whole thing. You just ignore all that. Why is that justified? That's justified because this is a much bigger part of the potential that you have to tunnel. And so if you calculate the rate in this limit, in which this picture looks like this, you will find that there's a parametric enhancement of that contribution. Okay. So this was the proposal in the 25 years old paper, that this is the way we will calculate these things. And so as promised, again, in some explicit models, when people calculated this, in the thin wall limit, so T is very close to TC, you find that there is an answer for the bounce action. The thing I want to point out is there is this parameter epsilon or lambda in the denominator. And this was the small parameter. This was what was making the potential so lopsided, and so the answer is enhanced by that. That's why this is a estimate for the bounce action. Okay. But the other thing to notice is that the bounce action scales as n squared in the numerator, which you expect. There is some small parameter that sits in the denominator, which is how these calculations were done. And then there is some function of T over Tc, which is a consequence of working in the thin wall. Okay. So the generic statement is like this, right? This rate is e minus n squared over delta. Delta is just generically some way to notify all this thing, and then there's a function. To trust this calculation, you need to be in the n large limit, right? So that hurts. Delta being smaller than 1, which is what all these calculations used, is basically saying that your CFT breaking is kind of small in the IR. So these are all parameters which are breaking the CFT. And then this being order 1 is the consequence of being in the thin wall. Okay, so all these things kind of conspire together to make the rate very small, and that's why this was all dead on arrival. So you can try to relax these assumptions and see what is reasonable and what will come out of it. So let's just zoom out on this.
Sorry, but isn't it more or less, if you want to be in a situation when semi-classical calculations can be trusted, then rate is going to be small. If otherwise,
well, so we will see. Yeah,
what small means for you, right?
So small compared to the Hubble, right?
Yeah.
And as we will see, when you go to the thick wall, you do tunnel out. There is a place at which you will tunnel out, but you don't want this temperature to be too close to BBN. So there are precise things that I can say, right? If I do not think about it from a phenomenological point of view, we'll say yes, it's a small rate. What do you want, right? But I want to actually use this into the framework, and then we will see that can we do it or not, right? How much of a straitjacket it is. So this is the general structure. What can you do? Well, one thing, of course, you can do is you can say delta can be made larger, and because the CFT breaking can be different in the UV and the IR, so just one parameter saying this is how much the CFT breaking is just a simplification. And this is what almost 99% of the literature in the last 20 years has done. Okay, with varying levels of sophistication, they have tried to change delta. Okay. And of course, changing delta translates to changing n in some way. So they say, oh, can this be viable for n equal to 2, n equal to 3, n equal to 5? This is how you can think of all the work. One is, of course, to go away from the thin wall limit, which has some technical complications, which reduces f, but not a lot. That also helps. A couple of papers have done this calculation away from the thin wall limit. Finally, you can say, well, you can also think about n changing from the UV to the IR, because that also happens in many examples that we know about. N in the IR can be different in the UV. Degrees of freedom can change in one way from UV to the IR, right? So that's another example. And I think this one has, I think there's one paper which tried to do something like this, but not explored much. But finally, you can say, well, all this calculation was done in this simplified radion picture, right? This estimate, this formula that I wrote down is in the radion effective theory. So what happens if you do not assume that? What happens if you say that radion is not the lightest mode and so you should not stay in the radion EFT? When this formula would not even look like this, right? So some other formula, some other calculation would have to be done. And anyway, all these things effectively run out of control and run out of radion EFT anyway, right? So you should maybe not trust this formula 100% in all situations. So now with this state set up, there are the two works that I want to mention. One is effectively about increasing delta and reducing F, similar to what many people have done, but I will try to argue that it's one of the most vanilla things you would do, which somehow people have not thought about. And then the second part will be a little bit more dramatic, which has more interesting consequences. So let's see how much gets done. So in the first part, we know that the CFT breaking in the IR can be different in the UV. And so in the 4D picture, the simple statement is that if I start with a CFT with some deformation, there is going to be a beta function for the deformation. The beta function can be small in the beginning. So if your scaling dimension of this deformation, which has a dimension delta, is very marginal, this term is small. But as this coefficient lambda starts bigger and bigger, you should include higher order terms, right? So as you start with a very small value of lambda and you keep going in the IR, at some point it becomes big. And now your theory should include lambda square, lambda cubed, everybody else. This translates in the 5D picture in which we model is to include higher order terms in the potential, in the bulk potential of a scalar, the scalar which is dual to this operator O. So this is scalar O is dual to a scalar field in the 5D, and having higher order terms in this beta function translates to having a more interesting potential in the bulk. And so the first work that I did is simply saying, take this term, which is non-zero now, and understand the effect of having a non-zero epsilon self-interaction on the whole picture of this phase transition business. Some part of the slide is cutting out. Anyway, so now let me be fast on the next couple of slides because there are details. If you're interested, I can tell you more. The specific potential we considered is a mass term plus a cubic, and there are some localized potentials you have to consider to fix the boundary conditions. The important thing is both these parameters are negative because this means that the effect is becoming bigger and bigger in the infrared. And then you can solve it in some approximate scheme. There are analytic solutions possible. The plots are showing that it's trustable. The analytic solutions match with the numerical solutions. Details. Okay. Long story short, you can calculate the radion potential with this self-interaction turned on. So there's a kinetic term for the radion and there's potential and this long expression for the potential. The thing I want to point out is here are 4 parameters: one with no self-interaction and one with varying amounts of self-interaction, and the potential has a minimum. But the important thing is that the location of the minimum doesn't change. It stays from 10 to the minus 17 to 10 to the minus 16. But the second derivative, which is related to the mass of the radion, changes a lot. Okay, so this is what this table is saying, that this phi min kind of stays, doesn't change much, but the second derivative changes a lot. And this we will see changes the bounce action by orders of magnitude and changes the rate by orders of magnitude. Okay, so this is the thing that I wanted to point out, is that the potential becomes deeper as you make the self-interaction bigger. And it's kind of expected because making self-interaction bigger is saying there's more breaking of CFT in the infrared. So this is going to make the radion heavier and heavier. So it's not a surprise. So you can calculate the phase transition for this, and in the first part, stay in the way everybody has done this calculation. Stay in the radion effective field theory, small back reaction. In the end, you have to solve for a bounce action, which is minimizing this action, right? So this is the radion phi, there's a potential, and this is subtracting the contribution from the false vacuum. After some rescalings that are useful to show the parametric dependence, you have to minimize this action. The thing I want to point out here is that this is how this n square dependence comes out. Planck scale is related to n, so this is how the n square dependence comes out. This was the breaking in the IR, which was a small parameter, and effectively the only information about anything interesting is in this function. Okay, otherwise everything will just drop out. You will just have some order 1 number here. Okay, so you can calculate this, and let me be fast with this. You can calculate this in the thin wall limit, the bounce action. You can calculate this in the thick wall limit. It was pointed out in that paper, I think 2 years back, how to calculate this in the thick wall. There are some non-trivial things you have to do there, but you can calculate it. And yeah, now once you have the rate, you compare it to the Hubble, which is what I was saying before, because the false vacuum is inflating. So the phase transition will complete when the rate is comparable to the Hubble, or effectively when the bounce action matches this quantity. I'm just taking the log of this quantity. So when the bounce action is smaller than this max bounce action, your rate is fast enough. The equality is what defines the nucleation temperature. Okay, so the bounce action is a function of temperature, and when the bounce action matches the max it can be, otherwise it's too slow, that's when the phase transition will happen. And effectively, because I said that the bounce action scales with n square, you can calculate what is the max n that is okay to have a phase transition. Okay. So these are the results for the first part, right? You for the same choice of parameters with non-zero epsilon, with 0 epsilon 3 but non-zero epsilon 3, you can look at the bounce action and as a function of temperature. This is the thin wall answer. Okay. This dotted line is the max, so the bounce action better be below this to have a successful phase transition. This, by the way, is scaled with n, so this is not bounce action, this is bounce action over n squared. Okay. So even for n equal to 1, this never happens. This is what was pointed out in the original paper, the thin wall. As you go to thick wall, it crosses at some point. If I make n larger, so this is for n equal to 1, if I make n larger, the curve shifts up, and now this crossing will happen at a different place. And the different place shouldn't be too far off if this critical temperature is TeV, and the nucleation temperature should not be below MeV. So 6 orders of magnitude, you shouldn't go below. And this translates into saying that if you want the nucleation temperature over the critical temperature to be, whatever, 10 to the minus 3, 10 to the minus 4, how much n is okay? If you make n too large, then the rate is too small, and then it's not interesting. N equal to 10 is barely within theoretical control, right? So this is what has been done in the past, and our work is simply saying you don't need to do something very sophisticated. Even a simple self-interaction in the bulb, which is to say CFT breaking is bigger in the infrared, will change the story at the same level that everybody else has done. Okay. So I think this is the first part, and if there are any questions at this stage, ask me, because I will go into the second part. Hopefully the setup is clear. There is a rate for phase transition which is too small, and you want to understand what are the parametric changes that are motivated to make the rate faster.
So these corrections to radial potential, you just put in by hand? Or?
Right now I put in by hand, and in fact the second part will motivate it on some UV examples, and we will see that the self-interaction will come out of it naturally. So that kind of says you should include self-interaction anyway. Yeah, but right now it's put in by hand. Okay,
so this is just to illustrate that kind of reasonably small self-interactions may change.
Right. Because everything is exponential, so even a little change in the bounce action will change. Yeah, like so. And just to say a few words about things that maybe phenomenologists care about, we care about a lot more, is that if you have this phase transition which is happening with a first order, with the bubble nucleation, there are gravitational wave signals that you will have, you will expect in this. A relevant quantity for that is this parameter beta over h, which is related to how the rate changes with temperature. You can calculate it. And here I'm plotting this parameter beta as a function of, I think, T over Tc. The interesting thing to note is that, so the blue curve is when there is no self-interaction, and the red curve is, this varying amounts of self-interaction. The important thing is that beta becomes very small or saturates. And this translates into the strength of the gravitational wave. So the gravitational wave peak frequency and the power carried by the gravitational wave depends very sensitively on beta. I will show you the next slide. And so it's saying that even this amount of self-interaction, well, it's interesting from its own theoretical right that it makes the phase transition faster, but it also changes the qualitatively what kind of peak frequency and amplitude you expect in this.
Can the story repeat with chi to the fourth, etc.? So
in principle, yes. And in fact, in the next part, when I will try to write down a potential which is motivated on some other grounds, you will see that it's kind of an exponential potential. So it's not just chi to the 3, it's chi to the 3 and 4 and everybody else. And there the picture will change qualitatively. So this is simply saying, look, this is how we do the calculation, let's do it with this. But when you include a more complete potential in some way, I think something more interesting will happen. So this is the sensitivity, the promised sensitivity that I was saying, that you can estimate, given beta, you can estimate the peak frequency and the power in the gravitational wave. The peak frequency scales with beta and the power scales with 1 over beta. And so if beta, instead of becoming small, kind of saturates, then these curves move, right? So instead of peaking here with this much strength, it peaks at a different place. And these two curves are for different values of n. So these are for different values of, this is for n equal to 2, this is for n equal to 5, or it translates into different values of when the phase transition happens. Different value of when the condition is satisfied for the phase transition to become feasible. Long story short, if you make the radion heavier by making epsilon 3 non-zero, your n max that you're allowed increases and your beta increases. This is the summary of what this works.
Wait, what was beta?
Beta was the derivative of the bounce action, and it's something that goes into estimating the gravitational wave signals. At least the contribution from bubble collision. There are other contributions, but they are usually harder to calculate. Bubble collision is the one that is much more under theoretical control. So the second part is we'll focus on reduce n, but actually it will we will see that it actually goes out of that equation that I schematically write down, e minus n square over delta times the function. It's out of radion effective field. So let's turn to actually explicit examples. What happens in many confining gauge theories, confining field theories, and there are supergravity examples that we know of. Usually they are not 5-dimensional, they have 5-dimensional plus additional compact dimensions, and these compact dimensions shrink to 0 size as you go from the UV to the IR. So for example, if the space-time is 6-dimensional, you have a circle in the 6th dimension, and as you go in the 5th dimension, the 6th circle is becoming smaller, 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 somewhere it just caps out, right? And from a 5D point of view, it looks like a model of the space-time just ended, right? You hit a wall. So we wanted to see, and there is another way to motivate the whole thing, which I will say in the end, but we wanted to see, right now the way I want to argue is, we wanted to see what is the effect of this, which is how it happens in many UV complete examples, on this calculation, because this is not how people were doing this calculation. Now, if it is true that there is a circle shrinking, then that means that the local Planck scale is changing as you go from the UV to the IR, right? Because the Planck scale is just, the lower dimensional Planck scale is higher dimensional Planck scale times the volume. The circle is becoming smaller and smaller, the volume is becoming smaller and smaller. So you can model that by making the coefficients of Ricci and the cosmological constant change as the scalar changes. Okay, so right now I'm still putting it as a model. There is a scalar with a kinetic term and a very simple potential. Epsilon is chosen to be negative so that phi starts with a small value and becomes larger in the IR. Right? So this grows. When phi is very small, you can just drop this term, right? Because it's 1 minus small number, it's 1. But as phi becomes bigger and bigger and bigger, at some point this effect will start becoming important. Okay. And so the goal is to investigate this model, and in particular, include the effect of back reaction, which nobody had done. And I will try to say why you have to include back reaction to see what we are going to see. Of course, that makes the problem much more complicated on the picture. Now, this is a messy basis to work in. You have Ricci, which is not constant. Things are tricky, so it's better to go into a frame where you rescale the Ricci, make the Planck scale constant. So you can do some wild rescaling. What means is that now this scalar doesn't have a canonical kinetic term, so there will be some kinetic term and the potential which will be changed after this Euler rescaling. So this is how it looks like. And then you can go to another field sigma where it makes it canonical, right? So you can make this canonical now. And this is finally the action that we studied. And there is some relation between this field sigma and this phi, and not super important. This potential looks like this. So with the choices that I was showing before, this potential has this cosmological constant part, which is the pure radius part, and then there is this exponential term.
But sorry, there is an interplay between n and m that makes it positive omega. If you go to the previous slide, the exponent of the potential in the second term is n and m.
This
Yeah,
n and
these
m,
two,
right?
yeah.
Yeah. So two things. One is that this expression that I wrote down for g phi and v phi, this is with general n and m, right? One is I'm going to choose this n to be 2 so that it makes my life easy. This is just going to become one function. So this is a choice. So far so good. But once I choose n, I could not have chosen 2, right? I could have chosen whatever. But once I choose n, I am going to demand m to be such that this effect is removed. Why is that? Because I want that when phi is very small, I want the potential to just be dominated by the cosmological constant. Right? The whole effect should happen in the infrared, not in the UV, right? So I want that I should choose my parameters in my phenomenological Lagrangian in some way, in a way that it reduces to the expected behavior in the UV. So there's some choice in M and M that I'm doing, and presumably if I changed a very different choice, yes, this might be different.
Are these choices that follow from, say, some supergravity?
So, not quantitatively, but qualitatively, I will show, since you asked it, in the end, once I get to the end of the results, once you look at the phase diagram that you get out of this potential, it will look very similar to the phase diagram that is calculated for the deformed conifol black holes. So if you look at the Kelvin-Strasser geometry with the smoothed out conifol, and you look at black holes in that, which would be an honest deconfined phase for the supersymmetric SUN cross SUM cascading gauge theory, there is a shape that you see, right? And we will see that it comes to very similar. And this way of looking at it will demystify many things. You will say, look, there is one simple potential, so can you understand everything in terms of this potential? And that's the way. So as I was saying, this potential will look like this, and this epsilon tilde is just related to the epsilon. I have just defined it for convenience like this. For large values of sigma, you can just drop this term, and you can drop this term, it just becomes a pure exponential. And for small sigma, when you expand, you see that you get this mass term plus cubic plus quartic plus all those other terms that I was talking about, right? With some specific relation between them because it's coming from some explicit model. Okay, so if we want to solve for this, it will change the standard answer on both the confined phase and the deconfined phase, right? What is the expectation on the confined phase? Well, in the limit of small pack reaction, if you remember, I said that the critical temperature is smaller than the confinement scale by this parameter epsilon. Now there is no epsilon, right? Once everything becomes equal to each other and things back react, so you expect that the critical temperature will be of the order of confinement. What is less clear is what happens in the deconfined phase, and this is the thing that I want to focus on. You expect that the free energy will change, but we will see that something more interesting will happen in the deconfined phase. How much time do I have? Sorry, 2, 15 minutes, 20 minutes. So we'll see how much detail I want to get into. But there is a way to set up the problem. So of course you have to choose some coordinates, and you have to look at the couple dynamics. This is the short shell metric. This is the the black brane or the flat short shell metric that we begin with. So the ansatz we begin with is to make the coefficients be a function of rho here. I'm going to be in Euclidean space because that's where it's easy to study thermal field theory. And we can now define rho to absorb this. So you can just make it a rho square. We can work with a better coordinate called C, which is rescaled in a way that the UV brane is at C equal to 1 and the IR brane, the horizon is at C equal to 0 because that allows expanding things easier. And so in the end, you have to solve for this metric. This is the ansatz for the metric. And you have to solve for this function K and D. Okay, there is a horizon at C equal to 0, so this is why this 1 over C sits there. This is a typical thing. And the horizon is at C equal to 0, that's why this TT component goes to 0, right? This is again the usual thing you see in black hole. A and B have the expected answer. The answer you can calculate when there is no back reaction, right? So you can calculate for A and B. And so the thing you want to solve is A, B, and also the scalar phi, right? Phi will also change, which will change A and B. It turns out you don't have to solve for B. B just is dependent on A and C, so you just have to solve for A and phi. And B drops out. It just depends on the other fields algebraically, so you don't need to worry about it. Oh, and there is this parameter alpha, which is just the location of, in some sense, the location of this with respect to this. So if alpha is very close to 1, then the horizon is very close to UV, and if alpha is very smaller than 1, then the horizon is very far away from the UV. Okay. The strategy to solve the differential equations, which is done numerically, is tricky because what boundary condition should you impose at the horizon? Right? Usually, when I give you a UV and IR, for people familiar with 5D calculations, you say here is the boundary condition in the UV, here is the boundary condition in the IR. But for the horizon, there is no boundary condition to be specified. All you require is that the fields be regular there. And what it means is that if you found the solution and you expand it in a Taylor series near the horizon, it should not have any blow-off terms. Right? So the field and its derivative should be smooth. So you can start with that. So if phi and A are regular near the horizon, C equals 0, so this thing. And it turns out that you can solve for each higher order term in this series expansion in terms of the first term, completely fixed. So if you just plug this ansatz into the equations of motion, you just find that phi 1 can only be one thing given phi naught, and A1 can only be one thing given A naught. In fact, this is what I'm saying here. A1 is fixed once you know A naught and phi naught. Phi 1 is fixed once you know A naught and phi naught in terms of the other parameters of the theory. So this gives you a way to solve for this. So this is the strategy. You start with some boundary condition in the UV. So remember, there are 2 scalars to solve for, second order differential equations, so 4 boundary conditions. You start with 2 in the UV and choose 2 other in the UV, solve for it, calculate these quantities here in the IR, the derivatives, and check that it matches. If it doesn't match, then you go back to the UV and change the parameters. And so you adjust the UV boundary condition till you satisfy the right thing that should happen in the IR. And so it's a little bit numerically intensive, but doable. And this is how you can solve for A and B and phi. And this is just showing you numerically that you can solve for phi, A, and B. The dotted lines of some choice of parameters, the dotted lines are the no back reaction case. And when you include back reaction, there's significant change, big order 1 change. A reduces, so phi grows more, A reduces, B reduces. Okay, so far so good. I'm going to skip this. Now now already we can start understanding the result and see what are the surprises. The first thing is this parameter alpha, which I was talking about, which is talking about how far the horizon is from the UV. The meaning of that changes. So if you look at the proper distance of the horizon from the UV, how far the horizon is from the UV, this is the formula by which you would calculate. And when there's no back reaction, it just scales as 1 over square root alpha. So smaller alpha means larger distance, right? Smaller alpha, larger distance. But since we know the solution numerically, we can calculate it. And what you find is that once there is big back reaction, the proper distance saturates. So the picture is that if I was a person dialing alpha, if there was no back reaction, dialing alpha meant this is the UV brane, the horizon just went like this. With back reaction, the horizon goes and it kind of just slows down here, right? The proper distance starts to saturate as you start making alpha small, which is different than the no back reaction case. So this is the thing that I wanted to point out here. More surprises. If you calculate the temperature now with this back reacted solution, so the temperature comes by looking at the smoothness of the Euclidean action and some details there. It depends on the function A and B that we know numerically. If there's no back reaction, this is how it looks like in terms of alpha. So again, small alpha means a smaller temperature. So as the horizon is further away, it's a lower temperature. That's the expectation. What you find is that the temperature actually has a minimum. So what it means is that the temperature drops in the beginning when the back reaction is not important, but at some point the temperature starts to increase as you dial alpha. Now, so far, alpha is just a bookkeeping number, like, this is something that I'm looking at. So what does changing alpha mean? Right? You can say, well, it's just a parameter which sits in your metric that you wrote down. What does changing alpha mean? So for this, you have to look at the entropy of the system. So remember, because this is a thermal deconfined phase, there is some entropy associated with it because we are at a finite temperature. A super quick way to calculate the entropy is to say, look, in the gravitational picture there is a horizon. We know area over horizon, area over 4g Newton is the famous Bekenstein-Hawking formula. That's the entropy. If you calculate the entropy, it depends on alpha. So area depends on alpha in the following way, and entropy depends like this. And it turns out that this formula is true independent of any back reaction. The simple reason is that the metric that I decided to work with is this. So when I'm looking at the area of the horizon, I'm looking at a fixed value of c at in time independent thing. So I'm only looking at this coefficient. It doesn't depend on a and b. So that will always have the same answer independent of what a and b are doing, okay, in terms of alpha. And so this is what alpha is telling you. You are changing the entropy of the system. And this is exactly what you want to get the phase diagram, right? You want to vary the entropy and you want to see what happens in the phase diagram. So smaller alpha means a smaller entropy, and this is not modified in the presence of back reaction. And this gives you a way to generate the phase diagram of your system. So once you know temperature is a function of alpha, entropy is a function of alpha, you can calculate temperature as a function of entropy and free energy as a function of entropy, and then we can compare to what was happening before, right, without back reaction. Once you know the entropy, you can calculate the free energy by this relationship, and let me not go into details, but this makes it much easier to do, which is not how the first paper calculated it. So, okay, so I think I already showed this. This is temperature as a function of alpha with the minimum. If you now look at entropy as a function of temperature, now it has a turnaround. It's a very weird behavior. So earlier the temperature was just dropping with the entropy was just dropping with temperature, but now the minimum temperature makes the entropy multiple value.
Value of temperature is
sorry.
So what? So something.
Yeah. So this is the now. In a couple of slides, I will demystify it because we see this all the time. It turns out it's just that you have to include back reaction in this version of the story to see it, but we see it all the time. So yes, it's already bizarre, right? It's already bizarre, but it's not bizarre in a very crazy way. It's just that the temperature has a minimum. So if you plot anything as something which is not
Sorry, what
multiple
happens
value.
if you plot the free energy as a function?
Next slide.
Because that's going to be more.
Right. So the free energy will actually have a kink kind of a thing, because it's the derivative, right? So instead of a smooth thing, you will now have like a little thing. And so the dotted lines are again, the dotted lines are the thing that you will have with no back reaction. Once you include back reaction, at some point you start getting a kink. And just zoom in on the thing. So it looks like this, right? It decreases, but once you hit the minimum temperature, it now goes in the different direction. And this free energy is always above this free energy, so this means that this is thermodynamically unstable. So what's happening, right? This black brain is or this horizon is receding, and at some point, the temperature starts to go up, and now its entropy is becoming less, or the free energy is becoming more. So it's becoming unstable, thermodynamically unstable. Okay. Which is totally not what people had thought about before. And notice, maybe I have a slide next, but this will change the whole story of the phase transition completely, right? Because the black brain phase or the deconfined phase needed to exist forever to talk about supercooling or problem with a small rate, right? Because you're stuck in the wrong vacuum. If the wrong vacuum has its own problem, then that's not the relevant thing to look at at some point, right? Once you hit this point. Okay, so summary so far is that there is a minimum temperature that happens because of this back reaction, and there are unstable branches of black brain solution. Now this analysis was so far numerical, right? So this is what we were sitting on 6 months back or 1 year back, and we were not sure how much to trust it. It turns out that you can do better. You can write down expressions for all these things in terms of one potential without even specifying the potential. So let me just say the results here. It's better to work in a different coordinate system for this case. It makes life easier. That coordinate system chooses the radial direction to be the scalar itself, because the scalar is just changing in a nice way. You can say that is my coordinate system. So in that, the location of the horizon is just a value of the scalar of the horizon. Right? That's what sigma h refers. And when you calculate how the temperature changes as a function of sigma h, so all these boxed equations are coming from massaging the equations of motion. That's it. Okay. You find that there is a sign change that happens at some point. So it had a certain sign to begin with when you did not have this potential, which is small back reaction. But once this term becomes big and crosses this, the sign changes. This is why you will have a minimum temperature, because the derivative is changing sign. This, it turns out, is the same term which shows up in the speed of sound squared. So speed of sound squared is just defined as this. If there was nothing else going on, entropy is supposed to scale as T cubed, right? So just dimensional analysis. So this would give you just 1/3. But now because of this back reaction, you get this term. And notice that this is speed of sound squared. So this will become, speed of sound will become imaginary at some point. You can calculate the specific heat, it changes sign. You can calculate the entropy over T cubed, which is a measure of degrees of freedom. And this is scales as 1 over the potential. So this is making clear the notion of how the N is changing as you go from UV to the IR. This potential is becoming bigger and bigger and bigger in the IR. And so 1 over the potential to some power is becoming smaller and smaller. Now all these equations have a plus dot dot dot. Okay, so this is dropping some terms, and this is a way to check whether these formulas match how well with the numerics, right? So this is something that can be said in a very universal way. The numerics was doing everything. But notice that all these formulas are done for a general potential. I didn't specify anything, right? So anytime you have an interesting potential which is important enough in the IR, you will have all these effects that will show up in the infrared. So yeah, this is just comparing the numerics and analytics, because the numerics are the full answer, the analytics are just using this part of, for example, speed of sound squared. When the back reaction is very small, it matches this 1 over square root 3. CS is 1 over square root 3. Once you start including the back reaction, they start to deviate but still kind of match. And for the cases with the biggest back reaction, the speed of sound squared becomes 0 at some point and negative at some point.
I mean, you have these ellipses there, so the next to leading term. So
right.
So these are subleading, or you can trust the point in which the potential dependent part cancels it.
So that's why this is not going to be exactly, yeah, good. So once this cancels, right, you were saying that this is going to be important, right?
Yes.
And that's why
because otherwise the fact that it changes the speed of sound is reasonable, right? You have a potential, the potential is like an effective potential constant, change the pressure. So
right. So I think you would have to look at the dot don't have a universal form. That's why it's harder to say anything precise. But so usually this thing, like dropping the dot is called the adiabatic approximation. You can say that. So I can tell you more about it. The term that I wrote down is coming from only looking at how the derivatives with respect to the scalar sigma r. But there is a second derivative, which is derivative with respect to sigma h, how the horizon responds to all this. And that's what the dot is hiding, how the horizon responds to this. At some point, those dot dots will become important. Okay, it may even happen that the minimum temperature will do even more crazy stuff if the dot are very important. Right? But for some choice where you want to have some control and the dot is not too big, you can trust the first part. And of course, it will correct the location. So I'm not saying that the 0 here and the 0 here are exactly the same, right? So there's some shift because of the dot. But it's telling you that the numerics and analytics are matching at least the places where you're putting them together. So, and this is me, sorry, in this expression, I'm just saying that if the speed of sound squared is this formula, we know what the potential we started with in the beginning, this exponential potential. So you can calculate it, at least in the limit when it's purely exponential. When it's purely exponential, v prime over v is just going to be a number, it's pure exponential. And you see that this indeed can become negative depending on your parameter. This strange shape that we saw for the free energy is just a consequence of the entropy being multiple values. So this can be calculated, with some very simple estimates that if S looks like this, then T as a function of S, if you turn it around 90 degrees, is just can be expanded near the minimum with a quadratic. And then you can calculate using this formula what the free energy looks like, and this fits the shape pretty well. So that's why the free energy is doing this funky thing. So there are qualitative differences. So now let's take a step back with all the things that we have learned so far. There are qualitative differences that are coming from the back reaction. The system shows a minimum temperature and leads to unstable branches. Now this unstable is twofold. One is that there is thermodynamically unstable, which is the statement that, so this is a cartoon of the thing that we calculated, is that this thing is always has higher free energy than this thing. there is local instability because the speed of sound is becoming imaginary. That usually means there is some tachyonic thing that is going to appear in this plasma at some point. Okay. Now, this will connect to another way in which I could have motivated the whole thing. This behavior is actually very generic. This existence of a minimum temperature is actually very generic. So the thing that I answered to Massimo earlier, if you look at explicit numerical solutions of Klebanov-Strassler geometry, which by the way are a tour de force because there are like 14 scalars and a lot more complicated dynamics that you have to solve, but people have done it. And there you find that there is a minimum temperature. Very clear, there is a minimum temperature and it's right close to the critical temperature. So there's not even much space between the minimum temperature and the critical temperature. And the minimum temperature depends on having an IR scale, which is this confinement scale. So here's the second example. We know this was all pointed patch of ADS. If you think about black holes and global ADS, which is a much cleaner system, you can do explicit analytical calculations. They also have a minimum temperature. And there's a critical temperature, which is the Hawking phase transition, and there's a minimum temperature. And they both depend on, again, an IR scale, the radius of the sphere. There is a third example which tries to study confinement in this indirect way. This is a paper by Igor Klebanov, where he studies not just this example, but also the Witten model of confinement, which is similar to another spatial circle shrinking, and more details about it. There too, there is a minimum temperature and there's a critical temperature, and they're all on top of each other. So it looks like this happens anyway in all good examples that we know about. And the reason I'm saying about this IR scale is because when people did all this calculation in the RS model for 20 years, on the black hole side, they never included the effect of the stabilization. Without the stabilization, there is no IR scale. So the only way you would know about this IR scale on the deconfined phase is by letting the equations know about the scalar. Right? If there was no scalar, there is no IR scale that is set. So it's not a surprise that you don't see the stimulus, right? And that's why it had to be harder to see because you have to solve the equations and whatnot. Yeah, so this is what I was saying, that specific to the RS case, there is no way to see the minimum temperature unless the information about the IR is put in. That means including the effect of stabilization on the geometry, which had not been done. Supercooling. So just to be a bit qualitative here, but existence of a minimum temperature means that there cannot be an arbitrary long period of supercooling, right? Because once you go past the critical temperature, depending on what's the difference, how much is the distance between the minimum temperature and the critical temperature, that's the most you can have, right? And so the picture is that, so in all these explicit examples, T minimum over T critical is order 1. There's no parametric separation. The general lesson that we're getting by this work is that if the CFT breaking is strong in the infrared, back reaction is important, then T minimum will be very close to T critical. So all these examples that people have studied, which was to have theoretical control over the calculation, it was a pathological thing because of wanting to write down a simple model that you found that there is no T minimum. Okay. What it means is that the first order phase transition is out. Right? If the phase itself doesn't exist, then there's no bubble formation, there's no gravitational wave, none of that. Okay. So that's depressing because that means that there was a signal in these scenarios it's out. It turns out that literally one door closes, the other opens. Because of this speed of sound instability, there are new sources of gravitational wave that people have barely explored. These are called spinodal gravitational waves, and people have written some first papers about it. And this is something that I'm thinking about right now. So even if T minimum is very close to T critical and the rate is too small to actually form bubbles and give you a gravitational wave, because the plasma becomes unstable at some point, there will be its own gravitational wave signals. And so the picture that I was drawing before, this is the UV brain, this is the IR brain. It keeps moving, and at some point it stops and it goes boom, it just explodes because all these instabilities have made every little fluctuation in it will grow and bound it. And at that point, what happens is not answered. So now this brings to my summary and conclusion. We have not answered the question about the dynamics, right? All we have done right now is drawn the phase diagram for the system, which is complicated enough. How does the system go from this, go through this instability, and does it settle down to this confined phase or not confined phase, and what are the signals, which is a dynamics question, is not addressed yet. And these are the things we're thinking about, and I think there are very interesting new signals that are waiting to be explored. I think I will stop here. Thank you.
So I suppose you may have said it, but the transition rate should still be small, right? Because it's in classical approximation.
So transition rate would be small here. But at some point, I'm not sure what to expect here. Right. So transition rate was small because it had an e to the minus n square, right? And that n square is literally the entropy, right? In some way, you are thinking about the entropy. But we saw that the entropy as a function of temperature is doing weird things at some point. So once I get close to this T minimum, I'm not sure what is the rate supposed to look like parametrically. This is the calculation that one has to do.
Wouldn't that the small n or n effective, wouldn't it mean also that in the bulk picture you have to take into account loops?
Yeah. You would have to include presumably everything. Yeah.
So how should one think about this situation? So let's say you're in the stable deconfined phase branch. Universe is cooling
Here.
as a function of yeah. Let's say at TeV temperatures, right?
Yeah.
So eventually, so as the universe expands, you get to 2 or close to T min,
right?
And you're saying that you leave the regime of validity of the theory, or
many things. So this is what my picture is, and there are explicit calculations that have to be done to support it. So you start with some very high temperature where, and this, by the way, is so an interesting problem because reheating has to put you there, right? So if the phase diagram is complicated, I don't know. Let's ignore that, right? Let's assume that inflation ends and you are here, right? So as the temperature redshift, you go like this, like this, like this. At some point, you are metastable, but the rate is too small. At least close to TC, the formula that I wrote, e to the minus n square should hold, right? So the rate is too small. So there is this plasma everywhere, and of course the plasma has fluctuations, but they're under control, right? But as the temperature keeps redshifting, at some point the speed of sound starts to become smaller and smaller and crosses.
Sorry, I should have asked before, but plasma of what? So this is now standard model plasma plus the thermalized.
The standard model plasma is always the plasma, and that's some small degrees of freedom. This is the plasma of this strongly coupled theory.
Okay.
Yeah.
So all of the light degrees of freedom.
Sorry, all the degrees of freedom of this strongly coupled sector. That's what that plasma is. That's the deconfined phase in which you are. And I'm saying that this deconfined phase, which is filling the whole thing, is becoming unstable. And close to this point, these fluctuations will do something. And from what I understand so far is that there can be inhomogeneous phases, so that it will clump into a little plasma here and nothing here, and a little plasma here and nothing here. And this is called the spinodal phase, right? Which is like a mixture of the two phases that you can have. And then at that point, it can do all kinds of things. I don't know, like these localized energy densities can source primordial black holes. The localized energy densities can do all kinds of stuff. I don't know precisely what it will do. It's also not clear how. I mean, it's presumable, but it's also not clear how. Once you go here, how are you going to land on this line? This is the confinement phase, right? So once this thing sputters out and becomes broken, is this just going to disappear and you will just be left with confined phase, or what? And this is what the dynamics has to answer. This is the rate calculation. Maybe it even has to include loops. I will have to think more about it. But definitely, the radion picture in which the calculations have been done is not correct, because that includes not including back reaction. And once you include back reaction, radion is as heavy as anybody else. So you have no right to just sustain the radion effectively.
Yesterday, Professor, what Mas said, there's some bad news about.
So this is